Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, let's take a look at lesson 7.3.2, labeled Describing Association Fully. And what we're going to do for this particular lesson is we're going to revisit a lesson that we did way back in chapter 1 with the roller coaster called Newton's Revenge. So let's just get to it. You have already seen that form, direction, and outliers can be used to describe an association. Today, you will complete the description of an association by considering strength. All right, so do you remember the Newton's Revenge roller coaster problem from chapter 1? You will now return the problem using your knowledge of y equals mx plus b to solve it. The problem is summarized below. If you recall, Newton's Revenge was a new roller coaster and has this tunnel that thrills riders with its very low ceiling. The closest the ceiling of the tunnel ever comes to the seat of a roller coaster car is 200 centimeters. Now that's a pretty sizable distance there, okay? And that's from the seat. So when you're sitting down, you would be reaching up, right? You can see the people that are reaching. So from where they sit to where they reach is a total of 200 centimeters of clearance. And so our task is to consider whether or not this is a safe ride for very tall riders. And we didn't get a chance to do it this year, but in years past and in years future, we will actually measure students in the classroom. We will take their height and measure it in centimeters, and then we will have them sit on the floor and measure their reach, lifting up their arms as high as they could possibly get to see what that distance is. And we're going to see if there appears to be a correlation or an association between a person's height and their reach. And if there is, then that's where we move to today's lesson, where we create a line of best fit and we create an equation to see if really tall people have anything to be concerned about. Okay, so to help determine whether the tunnel is safe for any rider, no matter how tall, you collect data in problem 24. Okay, so this is not the data that we used, but this is data that could have been used in our class. Height and the reach were both measured in centimeters. Use the data from the class at the right. Okay, so which is the dependent variable? This is what we want to get better at. Remember, one of these has to be x and one of them has to be y. Which one is the independent variable, the x, and which one is the dependent variable, the y? Well, what we're trying to do here is see if the height of a person has any sort of connection to their reach. So in this case, the reach ends up being your dependent variable, because we're going to measure your height and see what effect that has on your reach. And you might have some outlier situations here. Think of it. A Tyrannosaurus Rex is really tall but has very short arms. And then gorillas are a bit shorter, but they have really long arms that reach down to the ground, right? And so, if you had two people that resembled one a gorilla and one a Tyrannosaurus Rex, they would be considered outliers. But for the most part, we're expecting there to be proper proportioning here of a person's height and their reach, where taller people tend to have longer arms and shorter people tend to have shorter arms, so their reach would be less. So I think we can agree that the dependent variable in this situation would be the reach, and the height is going to be the independent variable. So when we create our graph, our scatter plot, we'll want the height to be our x-axis and our reach will be our y-axis. Hold on for one moment. I'm noticing my battery is going down. I'm going to pause and plug in. Okay, so your task is this. We are going to take this table with the height being your independent variable and your reach being your dependent variable, and we are going to create a scatter plot. So remember, our parameters, we want our scatter plot to go out to a maximum height. In here, it looks like it's 172.8. And for our maximum reach, it looks like it goes up to about 139. So I have that going up to 140. In order for us to identify the equation, we need to be able to find the y-intercept, which means you should set your graph up. Don't do those little break things where you start counting your reach at 110 and then you go up from there. You'll get your, you'll be able to see the data and the trend line fairly good, fairly well, but you're not going to be able to identify the y-intercept. So it's really important that we have the origin in our graph. So please go ahead, label this Newton's revenge. Your reach in centimeters is on the y-axis. Your height in centimeters is on the x-axis. And then once you've got this graph, please go through and plot each one of these ordered pairs on your graph. Take some time and do this nice and neatly. Okay, I'm going to pause, and when I unpause, you can unpause, and we'll do the reveal. All right, how did you do? Let's see if yours looks similar to mine. Oh, hold on for a second. Okay, I'm ready now. So I'm going to do the reveal. I'm going to do the reveal. Come on, reveal. There we go. Sorry. Okay, so all of our data is clustered up here. So this is one of those reasons why some people, when they create their graph, might have it start at 100 and 100 here, so you can get, it spaces it out a little bit. But we need this y-intercept. Now, following the trend of the data, it kind of looks like it does go toward our origin, right? And that would make our rule a lot easier because now it becomes like a proportional type situation. And I feel like that makes sense that 0, 0 would be the would be like a point on this line of best fit, because if a person is 0 inches tall, aren't they going to have no reach? Right? And if you think about that tiny cell that's developing as a human being before, only a few weeks old or whatever, they're pretty much going to be 0, 0. And then as it starts to grow, you start to get that relationship between height and reach with the length of the arms. So our task now is to find a couple of points on this line of best fit to see if we can figure out what the slope ratio is. Okay, so your next task, now that you've got your line of best fit, is find a couple of lattice points. And what could we use for lattice points here? Let me color code these guys in blue. Definitely I'm going to use 0, 0. And I don't know. I don't know what to use here. Oh, that one looks like a good one right there. Let's try that one right there. This is where x is equal to 130 and y is equal to 100. So what appears to be our slope ratio? Go ahead and see if you can figure that out based on the fact that this is the origin, which is 0, 0. Figure out your change in y over your change in x and write that as a decimal number or as a fraction. Okay, let's see how we did. So if you take your change in y over your change in x, in this case to go from 0 to 100, right? That's the y value is 100, so that would be 100. And your change in x would be 130. So that ends up being your slope ratio, which could be changed to a slope of 0.77. Now, watch what we get here. Oh, let me get some work out of there. If you take 100 and divide it by 130, you're going to get a repeating decimal, but that's really close to 0.77. Now, let's say I actually decided to have this be my line of best fit, where I chose to have that be a lattice point, which is where x is equal to 180 and y is equal to 140. Right? 180 and 140. How would that change my slope ratio? That would mean my change in y would be 140 and my change in x would be 180. And if I take 140 divided by 180, I get it's like 0.78. So 0.77 versus 0.78, there's not much of a difference there. And so your line of best fit does not have to be perfect. It's hard. I mean, what is perfect? We don't know. But that's a pretty good line of best fit. It goes through the data, follows the trend of the data. 0, 0 makes sense. So I'm going to stick with our first one that we did, the slope being rounded to 0.77. So that's what we're going to use for our rule. Okay, so this applies. And basically what this rule is saying is if you change this slope ratio to a percent, it's really telling us that a person's reach is about 77 to 78% of their height, right? And their reach being measured from if they're sitting in a chair, from the bottom of their seat to a straight extended vertically fingertip. What would that distance be? So your reach tends to be about 77 to 78% of your height. So let's now decide if this is a safe roller coaster. Okay. So for people of average height, all of this, I mean, the danger zone was at 200 centimeters, right? And we didn't have a single person that was over 139 centimeters in reach. So that gives you lots of room. That's like 60 centimeters of clearance, and that's with the tallest people. Okay? So, but this is a normal classroom kind of a setting. This does not include like basketball players. So would this be safe if this is the general rule for all people? Would it be safe for someone like Yao Ming? Okay, so it says once you have the equation that can best represent the data in problem 97, you will be able to use the equation to verify that the roller coaster is safe. The amusement park wants Newton's revenge to be safe for all tall riders. For example, Yao Ming, who used to play for the Houston Rockets and then the Toronto Raptors for a short period of time, he was 7'6", which if you convert that to centimeters is about 228.6 centimeters tall. So would he be safe? Okay, so keep in mind, the tallest people here were only right around there. Okay, so he is significantly taller, so that means we can expect him to have a significantly greater reach. So let's go ahead and solve the problem. Let's go ahead and plug in these numbers. If we multiply 228.6 times 77% or 77 hundredths, what do you get? Go ahead and use your calculator to figure that out. And if you're just going to wait for me to reveal it, you're in luck because I'm going to reveal it right now, and it's going to say 178 centimeters or 176 centimeters once you round it off. Okay, so the tallest person in the NBA, which is made up of very, very tall people, still has about 24 centimeters of clearance, which is a little bit nerve-wracking, but it should be safe. So we can go ahead and say for most people who aren't super, super tall, we would recommend that they could go on this ride without having to worry about hitting the top of that tunnel. Okay. Now, if you are super tall, like 7 feet tall or taller, exercise your own judgment. And I think that's what most amusement parks do. They will say, you know, if you got to be this height, but if you're taller than this, you probably shouldn't go on this ride, and you should honor those signs. But you know, it seems like this is reasonably safe. So the slope and the y-intercept can sometimes give you more information about a situation you are studying. Sometimes their interpretation makes no sense. So, you know, in this particular one, for my line of fit, I feel like the y-intercept did make sense. What is the slope of the line of fit? And interpret this in the for this particular meaning. Well, the slope was 0.77, right? And interpreting it means that a person's reach is about 77% of their height. Does this interpretation make sense? It's like, yeah, I think it makes sense because your reach is almost always less than your total height, unless you're a gorilla. So, and we're not, so that should be fine. And then interpret the y-intercept in this situation. Does that make sense? Now, I said that the y-intercept was about 0, and for me that does make sense because if you're 0 centimeters tall, you would have 0 centimeters of reach. But as we saw in some other scatter plots, sometimes it just doesn't really seem to make a whole lot of sense. So please follow the data, and sometimes your y-intercept will appear to not make much sense. Other times it will make sense. And in this case, I think it does make sense. All right, so last bit of information. Remember, strength of association. The closer your points get to your line of best fit, the closer your rule or your equation for the line of best fit will help you predict outcomes in these situations. Okay, so this is an example of a negative slope, and if you look, those points really come very, very close to our line of best fit. It's easy to find the line of best fit here because there's such a strong association with this data. As you start to get these points, spreading out a little bit more, it weakens the association. So this is still a negative association, but it's more moderate. So your line of best fit will be sort of like an average, but you'll want to have like a little bit of flexibility with your answers, like plus or minus a few number of infections for the annual hours of nursing training. What is that? Number of infections in hospital? And I don't know what that means. That's a weird set of data. And then college GPA and your SAT score. Is there an association there? Well, it appears to be positive, right? The higher your SAT score, which is a test score, the higher your grade point average tends to be. But it's a weak positive association because there are so many other things that influence your grade point average. Like, you can be really smart, but if you choose not to do any work, you're probably going to get a lower GPA. Or maybe you've got people over here who didn't get a good score on their SAT, but they're really hard workers, and they're always doing their homework, and they're always trying their best, and they retake tests whenever they can, and so their grade point average goes up. So the farther away these points are, the weaker the association. The closer the points are to your line of best fit, the stronger the association. Okay, so fully describe the association in Newton's revenge. Well, I would say that this data was moderate, right? I think they were relatively close to your line of best fit. It was linear, it was positive, and I did not see any outliers. I mean, this one comes close to an outlier, but it's not like here, or it's not like here. So those would be clear outliers. I don't think there's any clear outlier there. So positive, linear, moderate, with no outliers is what I believe is the full description of the situation. Positive, moderate, linear, no outliers. All right, so that does it. And I'm trying to decide if we're going to do lesson 7.3.3 because it's kind of a confusing lesson. And I don't know if we're going to go there. I think in years past, I've just skipped over it because it's really not related too much to what we've been learning, or it is somewhat related. It's also somewhat complicated, so we'll see. At any rate, let's head to our next activity, and we should be winding on down and getting ready for a chapter test. So take care. Bye.
Hey, feeling good, like I should. When in dark,